So in this video we are going to talk about our last quantity, acceleration. Now in all of the previous videos we talked about various quantities like distance, displacement, velocity, motion. All of these things were uh, talked about or discussed in the previous videos. Now even after learning so many of terms and so many of quantities, what was the need for another quantity? Why this another quantity of acceleration was needed, or why it was actually necessary to derive one more quantity? Was there some purpose, or was there some immediate need which couldn't be solved without introducing the concept of acceleration? See, when we talked about distance, see, firstly, in the first video we talked about motion, right? When we talked about motion, we came to the conclusion that motion actually equals to change in the position of a body, or change in the position of an object. And then after that we needed to define some quantities through which we can verify or confirm that position has been changed. So we needed some quantities which could define our change in position. And what were those quantities which were actually able to describe the motion or able to describe the change in position? These quantities were distance and displacement. So we actually studied distance and displacement. Now we actually wanted to after this part we actually wanted to know about the rate of change of position, that at what point or through what concept our position could be changed. Now we know that some amount of time is definitely needed to change our position, right? If you are here and you need to go from here to some point here, you will require some time, right, in order to go from here to here. So in order to actually describe or find out that in how much time a position will be changed, we needed to know about rate of change of position, right? And that rate of change of position was actually given to us by velocity, by the terms velocity and speed. So that was the main reason why we studied speed and velocity, because we actually wanted to know rate of change of position. Okay, so after studying all of these, we came to the conclusion that speed also changes, right? Speed will also change, velocity is also will also change. It will not stay uniform for longer period of time, because such kind of motion is not ideally present in this universe. Yes, it may be present in this universe, but it is not actually feasible or practical to for a body to always travel in uniform motion or in uniform speed. So we needed to find out the rate of change of velocity or the rate of change of speed. So for that particular thing, rate of change of velocity or rate of change of speed, we introduced such another term or one another term which came to be called as acceleration. So this was all the history behind the term acceleration, or the story behind why we actually study acceleration, why it came into being, right? So acceleration is what, like I've written here, rate of change of velocity. So acceleration is defined as the rate of change of velocity. Now let's try to understand this by using a very common example. Like, you already know that when a car is traveling on a road, it is not possible for that car to actually travel with uniform velocity. Is it feasible for that car to actually travel with uniform velocity? No. We talked about this in the previous video as well, right? When we were talking about the case of uniform and non-uniform motion, we came to know that whenever you're traveling on road, your speed actually depends upon situation and circumstances, whether how many obstacles you are actually facing. So same is the case here. So we know that whenever you're traveling on a road, you may not be able to always travel with uniform speed. Your motion is going to be very much dependent on the obstacles and the kind of things you are facing on the road. So let's take another one such example. Now we are not going to concentrate on the case of the cars. Now let's try to think about a train. Let's think about a train. I'm going to consider this as my train. Okay, this I'm gonna consider as my train, and let me suppose that now we know that initially this train is going to be at rest, right? Initially this train is gonna be at rest. Initially at rest. Understood? Now if it was initially at rest, but when we want this train to be in motion, it's gonna pick up speed, right? It is gonna pick up some velocity. You can use term speed or you can use term velocity, one and the same thing. The only difference is that whenever you use velocity, you need to specify the direction as well. So let me think that this my train, which initially was at rest, starts moving, and when it starts moving, its speed or its velocity, which was zero, which was then zero, started increasing, right? It gained some velocity. Its velocity increased when it started the motion, right? When it started to move. So now it has which my train, which was initially at rest, now after moving, it gained some velocity, right? And what I see that after moving some certain amount of distance, this now my train is going to move with a constant velocity. Now it will keep on moving with a constant velocity. Like let's imagine this scenario, right? Let's imagine this scenario. My train, any train, let's suppose that a train, it was initially at rest. When it started moving, it gained velocity, right? And after traveling about some few minutes, it actually kept a constant pace and attained a uniform velocity and started moving with that particular uniform velocity, right? With some that particular uniform speed. But now what happened is that its destination came in front of this train. The station at which this train needed to stop was closely approaching. Now what this train is going to do, definitely when it is going to reach this station, it is going to slow down its pace. It is again going to decrease its velocity, right? This train is now going to decrease its velocity, and when it arrives at its destination, it is going to again completely stop and be at rest, right? So let's just quickly review this scenario which we've established. What happened was that when train started moving, I know that my train starts from rest. Like when my train starts from rest, its speed increases from zero, and then I say that what my train has done, it has actually accelerated, right? The literal meaning of this term acceleration is actually it actually means increasing, to increase something, right? So here it has increased. My speed, my velocity has increased, so acceleration has been uh, taken into account. What has happened here is that some acceleration has occurred. So I say that when train starts from rest, its speed increases, its velocity increases from zero, and we say that train is accelerating, right? After some time, what happened was that speed became uniform, right? When it traveled a certain amount of distance, right here the speed became constant, okay? And then I say that my train is actually moving with uniform speed, okay? That means moving with uniform speed, that right now no acceleration is being occurred. Right now there is no acceleration taking place. But as the train is nearing the station, it slows down, which means now the train is accelerating in the negative direction. That means, why this happened? Because when the train is nearing the station, it slows down. Its velocity, its speed decreases. If its speed decreases, that means it is accelerating, but not in the positive direction. It is accelerating backwards. It's now decreasing its velocity, so it is accelerating in the negative direction. That means whenever some object's velocity or speed increases, we say that that object is accelerating in the positive direction. But whenever the speed is decreased, we say that now the object is accelerating in the negative direction, right? So now you know what has happened. So actually that means the literal definition of acceleration, the literal meaning of acceleration was to increase, right? To increase. But now from this explanation, we came to know that in physics, acceleration does not only mean, or it need not only mean, that your speed or whatever you are considering, whatever quantity you are considering, is going to increase. So here acceleration not just means that your speed or velocity is going to decrease. It can also mean that your velocity is decreasing or remaining same, or actually your acceleration or your velocity is zero. Okay, so that means what I can say is that the acceleration need not always mean that speed of the moving body is always increasing. It can also decrease, remain same, or maybe even zero. I hope this acceleration concept is clear to you through this example, right? What happened was that we come to the conclusion that yeah, their speed is increasing, so it is accelerating. Whenever your speed is increasing, you are accelerating. After that, here in this part, the speed became constant. The speed didn't increase. So we say that now the speed has become same. Now it is moving with uniform speed. So there is no acceleration, no acceleration. Okay, and after that the speed actually decreased. So we did that. Now what has happened is that it is accelerating, but actually in the negative direction. So we came to know that acceleration can remain. So the speed can remain actually zero. Speed can actually increase. Speed can also decrease, right? So acceleration means all of these things: your speed increasing, your speed decreasing, your speed remaining same, or even your speed becoming zero. So now mathematically, if you want to write acceleration, I've already said it is rate of change of velocity, right? So that means acceleration is v minus u upon t. If I consider v to be my final velocity and u to be my initial velocity, so obviously acceleration is going to be change in velocity upon time. Do remember that it is a vector quantity, because it actually talks about velocity, and velocity has some direction. It is a vector quantity, and acceleration also has is also bothered about the direction as well. So it is a vector quantity. Acceleration is a vector quantity. Let's quickly talk about its unit. You already know what velocity's unit are. Like here in the numerator we've got velocity, and its units are meter per second, and again we've got time, we take it in seconds. So what we get is that meter per second square. So acceleration's units are meter per second square. Okay, so with this your acceleration part is complete, but we got to know about the types as well. So acceleration has a lot of types. There are many types. So right here I've got my positive acceleration, after that I've got negative acceleration, I've got zero acceleration, and the last two types, uniform acceleration and non-uniform acceleration. Now you know about positive acceleration. Yes, accelerating in the positive direction, that probably means your speed increasing. Yes. So what do we say when positive acceleration is happening? If velocity, right, if velocity of object increases, then the object is said to be moving with positive acceleration. If the velocity of the object increases. Now if the velocity of the moving object decreases, if velocity of the moving object decreases, then we say that it is moving with negative acceleration, right? So negative acceleration, or you can also say that in that situation what is happening is retardation. So decreasing speed also means retardation or deceleration. Deceleration, right? Do remember the term deceleration, because it means retardation as well, or negative acceleration as well. So negative acceleration or retardation or deceleration. What are these three things? These three things actually point to the same thing, that is speed of your moving object decreasing. Now let's talk about zero acceleration. Yes, when can zero acceleration occur? Didn't we talk about the case of the train, when after moving a certain distance or certain amount of time, my speed of my train became constant? Right here, didn't I say that after it was at rest, then it started moving, it gained some speed, but after traveling some time, it achieved a momentum, it achieved a constant pace, and then started moving with uniform speed. So when this train was moving with uniform speed, did I say that some acceleration was occurring? I said that no acceleration is taking place here, right? I said that. So zero acceleration case is right here. So whenever either your object is at rest, whenever your object is at rest, or it is moving with actually uniform velocity, whenever your object is moving with uniform velocity, or it's actually not moving at all, that is, it is at rest, you say that your object is actually your object actually has attained zero acceleration. So let me put it in more finer terms. If the object is at rest or moving with uniform velocity, then object is said to have zero acceleration, right? You now understand about positive, negative, and zero acceleration. Now we are going to talk about uniform acceleration and non-uniform acceleration. So yes, whenever we talk about something being uniform and something being non-uniform, we always consider the case of distance and time, right? But right here we're not going to consider distance. When we are talking about uniform velocity, we said that this type of velocity has been covering equal distance in equal intervals of time, right? But right now I'm dealing with acceleration, so I'm not going to use the term distance. Right here I'm going to use the term velocity. Yes, that is correct. For uniform velocity, when an object is said to be in uniform velocity, probably it's quite simple. If it's moving with what it is, if it is moving with same velocity. I've written here equal, there is no need to write equal. Actually, the more final term would be if I say that if rate of change, if change, actually uniform when your change in velocity is same. If your change in velocity, right, when uniform acceleration is attained, when change in velocity, that's right, change in velocity is equal. Okay, if the change in velocity is equal in equal intervals of time, we say that our object is in uniform acceleration. And what about non in uniform acceleration? The same scenario, but here your change in velocity in equal intervals of time is not going to be same, right? Your change in velocity, whatever change is happening in the velocity, whatever change is happening in the speed in some amount of time, in some interval of time, if that is not going to be same, then we say that our object has actually attained non-uniform acceleration. So when we put it in finer terms, in more pure terms, we say that if the change in velocity in equal interval of time, if the change in velocity in equal interval of time is not same, it is not same, the value is actually changing, then the body is said to be moving with non-uniform acceleration. So let me repeat it for uniform as well. Now, if the change in velocity in equal interval of time is same, right? Focus on the same, then we say that object is moving with uniform acceleration. Right here, this was the case of the train when it was on the road, when the road became smooth, when there was no obstacle for it, when it already had started, and it had actually moved up for some quite amount of time, then we said that our train started moving with uniform velocity. So in this case right here, there was the case of zero acceleration, right? So what happened now, if I suppose that my car, see, if you've got a table, if you've got a complete data of something, right, you've got a complete data of something, and what you're finding is that your rate of change of velocity, is actually coming about same. If this is my rate of change of velocity, let me say that this right here is my rate of change of velocity, and this right here is my time, right? And I say that first 10 second, then 20 second, then 30 second, something like this. So this data is actually for every 10 second, right? For every 10 second. And my rate of change of velocity right here is that, let me say, suppose that here it was 20, after it became 40, then it became 60, you can say kilometer per minute or whatever, right? So you find a regular pattern that for every 10 second the rate of change of velocity was 20 something, 20 kilometer, right? So that's this is actually the case of uniform acceleration. Okay, I hope now it is clear what when an object happens to be at uniform, when at non-uniform, or this amount of time. See, do not actually mix uniform and zero acceleration. Please do not mix uniform acceleration and zero acceleration. Zero acceleration arises only when your object is at rest, or it is actually moving with uniform velocity. That is, your velocity is not changing, your velocity is remaining same. But actually in uniform acceleration, there is going to be change in some velocity, there is going to happen some change in velocity, but that change in velocity, whatever change in velocity is happening in some amount of time, is going to be same. Like for this particular first interval, 0 to 10 interval, the rate of change is 20, change is occurring but it is 20. Okay, for another, let's say 10 to 20, the change was 40, right? The change was 40. So actually 20 kilometer change is occurring at every 10 second. So this was the case of actually uniform acceleration. So for your uniform acceleration, there is definitely going to be some change in velocity, but the change in velocity in equal interval is going to be equal, that is same. So this concludes our topic about acceleration and whatever types of acceleration there are. Next, after that, we are going to actually discuss a very important part, which is graphs. There is going to be distance time graph, velocity time graph, and also speed time graph. We are going to discuss about these three types of graphs. After that, there are going to be equation of motions as well.